We're going to talk about Chapter 5 tonight and look at some other ideas regarding construction equipment and productivity. So we've been looking at not only how to cost out equipment so far, but how to apply that equipment cost to the cost of actually doing work. So there are a number of methods. We looked at some basic methods starting in Chapter 4. And there are a couple more ways we're just going to touch on. Again, the idea being, in part, that you understand that there are many different ways that you'll possibly see regarding costs. Tonight in particular, we're going to look at Purifoy's method of optimizing productivity. And what's important about the method is that, again, it considers a lot of different factors. And we've looked at some of the factors so far. But in particular, there are 9 that Purifoy looks at. Haul road rolling resistance. And that, again, we've been talking about how smooth or rough a road is. We're looking at haul road grades. Remember, it's easier to travel downhill than uphill, and depending on if you're loaded or unloaded, it makes a difference in terms of the speed of a vehicle. We look at the horsepower, or the amount of power that a vehicle has to actually do work or to transfer power through either the wheels, which is what we refer to as rim pull, or through a drawbar when we have a tractor pulling a piece of equipment. Other things that are important are the loaded and empty weight of a piece of equipment. The transmission characteristics, and particularly I don't think you think about a lot, especially in the days of automatic transmissions, but most of the equipment we're talking about are modifications of manual transmissions and automatics combined with manual, but there are different gears, and each of those gears has a purpose, and how you move through the gears affects the speed that you're going to be going, and certainly then the productivity. We look at the loading time. It takes time to both fill up a piece of equipment and to empty a piece of equipment, so you need to know about those. There are efficient ways to do that and inefficient ways. Haul unit travel time. Again, how far you have to move a load once it's filled, and again the return time to come back are important. Haul unit delay. There's always a lot of places where time can be lost or wasted in the complete cycle. Remember, the cycle is a vehicle's in place, say a truck, by the loader. Then the loader starts filling it. Once the loader fills the vehicle, then the vehicle travels down to wherever it's going to dump its load. At that point, it dumps its load, turns around, travels back, and then pulls back up to the loading equipment. That's cycle time for that process. Now, the loader itself also would have a cycle time. The loader will be by the truck, then the loader is going to move to the pile that it's filling. It'll fill the bucket, it'll back up, it'll go back to the truck, it'll empty its load, and then the cycle will start again. One last factor that Purifoy considers is altitude, and altitude affects performance. Just like humans, you need a certain amount of oxygen to make an engine work efficiently. Now, in the days in past, it was a little more critical. With modern engines, computer controlled, a lot of the adjustments are made automatically. As it moves, the computers change the mixes of fuel and air to accommodate the altitude differences. And I mentioned a minute ago rim pull, and rim pull is the energy that's transmitted to the wheel of the vehicle and then down through the tires to the ground. So rim pull is just a measure of the energy that can be used to move a load, and when you look at rim pull, it's a function of a couple things. HP, which is the horsepower, and then E, or small e, which is the efficiency of the engine. Engines aren't 100% efficient, and you have to account for that. And V is velocity in miles per hour. Also, when you have grade and rolling resistance, the amount of rim pull required is a function, again, of the weight of the vehicle in tons, the W, RR, which is the rolling resistance, and we looked at that last week, and S is the slope of the grade. So as the grade increases, you'll see that the rim pull required increases too. If the grade is negative, or you're going down slope, you can see that the rim pull becomes smaller. The difference between the maximum rim pull and the required rim pull equals the amount of force available to accelerate the vehicle to top speed. In other words, the difference between these two equations, 5.1 and 5.2, gives you equation 5.3, and it's the acceleration that is important. The faster you can accelerate, the faster you can get up to speed, and the speed that you're going to be moving from point to point. So if you take a half a mile to get up to speed because you can't accelerate very fast, that's a real problem, as opposed to if you can accelerate to a quarter mile and get up to speed. Obviously, you're going to get up to your travel velocity a lot quicker, and you'll be able to get to the other end of the trip a lot quicker too. 5.1 is an example of this, and it's just looking at a small truck with a 150 horsepower engine with an efficiency of 0.81. Again, the efficiency goes to altitude, condition of the engine, things like that. And you're going to make an estimate that a brand new engine will get close to 1, but after that, and depending on how well you take care of it, the efficiency goes down. The vehicle weighs 38,000 pounds fully loaded, and it has 5 gears in the transmission. And again, this is probably a manual transmission, although you can have an automatic transition that you can shift through the gears, and many of the modern trucks are like that. But each of the gears has a maximum speed. So first gear has a maximum speed of 3 miles an hour. Second gear, maximum speed of 5.2 miles an hour. Third gear, maximum speed of 9.2 miles an hour. Fourth gear, 16.8. And finally, up to fifth gear, 27.7 miles per hour. And what you're interested in is time to reach that speed on a level road with a rolling resistance of 60 pounds per ton. Okay, and we looked at that rolling resistance last time. So if you go back and you subtract equation 5.2, you can remember that was the one that accounted for grade, from equation 5.1, fill in the blanks here: horsepower, efficiency, velocity, slope, rolling resistance. It tells you that the maximum available rim pull per ton is 739.34 pounds per ton. Again, because of efficiency, especially in the transmission, you don't often get to that maximum rim pull. And if you notice in the book, the author also says you don't often get to the maximum rim pull because of lack of driver courage. Well, I think you don't necessarily want the bold driver that accelerates too quickly when the conditions are correct. So that's a little bold. But when you account for those facts that drivers are different. They don't always accelerate at the maximum. That you really the maximum value of rim pull is 300 pounds per ton, and that's what Purifoy cites in his book. So if you then go to equation 5.3, you can find that maximum acceleration is 198 miles per hour per minute. So the time to accelerate from 0 to 3 miles equals 3 miles per hour equals 3 divided by 198, or 0.015 minute. So you can do the same kind of calculation for each of the gears if you keep the 300 pounds per ton as a maximum, and then it will tell you how quickly it would take to get all the way up to 5th gear. So if you assume there's 4 seconds per gear change, and what that usually involves is pushing in a clutch and moving the gear shifter around and then letting the clutch out, and that happens 4 seconds every time you change gears between 1 and 2, 2 and 3, 3 and 4, or 4 and 5. You'll find that the total time to accelerate to the top speed of 27.7 miles per hour, remember that's the top speed for that 5th gear, is about 1.069 minutes. And what this number really tells you is that getting up to travel speed isn't an instantaneous thing, and anyone who drives on their car on the highway knows that you don't get up to the speed limit, say if you're sitting at a stoplight when it turns green. Instantaneously, you're going to be going some distance down the road, and again, if you have a stick shift, you'll be moving that stick, but if you have an automatic transmission, you'll know that you'll be able to feel the gears changing as you go up, usually through 3, possibly 4 gear changes. Now that time to accelerate up to speed is just one part of that cycle time, and it's part of actually the travel time back and forth. If we're really going to look at the total cycle time, though, we have to consider a number of items, and we've talked about them so far, right? Total cycle time is C. L is the loading time in minutes, and we talked about how long it takes to load a vehicle up. T is the travel time, and it's going to have be a function of that acceleration time that we just calculated. And D is the discharge time. Plus there may be some other time, again, for maneuvering the truck around, just lost in travel, that you're going to add. A loading operation on a construction site isn't going to be a smooth operation. So again, L is in minutes, T is travel time is minutes, D is in minutes. What we're interested, though, really, when it gets all said and done, is the optimum number of haul units, which is N, that you need to make an efficient operation. And that calculation, simply a number of units, N, is simply C, the cycle time, divided by L, which is the loading time. And when you have N, then you can estimate the productivity, where productivity, P, is in tons or cubic yards per hour. And SH is the size of the hauling unit. Again, it might be tons or cubic yards. And 60 is a conversion factor, but you see you'll be able to get the productivity is a function of the number of hauling units and the cycle time. That makes a lot of sense, and it's straightforward. So if you have an 18 cubic yard dump truck and it has a loading time of 3 minutes, a travel time of 7 minutes, and then it takes 5 minutes for dumping and other miscellaneous delay, you can calculate the cycle time and the optimum number of units and productivity. So see the cycle length is 3 minutes plus 7 minutes plus 5 minutes, a total of 15 minutes. So if you have a 3-minute loading time, you can get the number of units, and by dividing that total cycle time, 15 minutes, by 3, which is the loading time, tells you you need 5 units. And again, think about this. It makes sense. If you're using a loader to fill these trucks, that loader is only busy for each individual truck 3 minutes. And the other 12 minutes, that truck is away, traveling, and then dumping its load. So during that other 12 minutes, you can put other trucks there and fill those. And if you use 5 trucks, then you can keep that loader busy continuously, and it's not sitting there. And then, of course, once we know the number of units, 5 units in this case, we can calculate the productivity by inserting the 5 in the 15 minutes of total cycle time, and you get 30 cubic yards per hour. So that's the productivity you can get with 5 units and a 15-minute cycle time. There's also another set of theory developed by Phelps that breaks the cycle into 3 parts: fixed time, variable time, and loading time. Okay, the fixed time consists of all the delays that are built into the system due to the mechanical problems and human factors, okay, the truck characteristics and the driver characteristics. So it includes acceleration and deceleration, turning time, dumping, and non-productive times. Looking at things this, you can find the acceleration and deceleration using empirical values that have been developed, where x is the number of accelerations here in the equation, and y, and x is when they're loaded, when the vehicle's loaded, and y is the number of accelerations when they're empty. So for total acceleration time, 0.3x plus 0.2y, and for deceleration time, 0.02x plus y. Besides that fixed time, there's a variable time, and in this case the loading time is estimated from production characteristics that you get from the manufacturer. Remember, we've been looking at manufacturers' characteristics for a number of vehicles, so that's if you're always wondering where do you get these numbers, well, there's 2 places. You can do a little study and time activities as they go on, or you can go to manufacturers' catalogs and equipment specifications, and you'll be able to find that information too. In this case, if you look at table 5.1, you can see in terms of fixed time and loading time that for short haul, and that's between 200 and 1200 feet, fixed time is 4.5 minutes plus L, which is the loading time. For a medium haul of 1200 to 5000 feet, just under a mile, again, F equals 4 minutes plus L. And for a long haul, which is 5,000 to 9,600, or about 1 to 2 miles, just short of 2 miles, the fixed time equals 0.35 minutes plus L. Obviously, see, the longer the haul, the more efficient, and that's why, again, when we looked last time at the distances that you'd use different equipment, that for hauls over about a mile or so, the trucks are really a good way to go. And what these equations assume is 1 acceleration and deceleration for each haul. When you start and you stop. In a return trip, same thing, a stop and a start. If you stop in between, and sometimes on a congested site you do stop more, then you have to increase the values in the formula to account for that. So if we go back to our earlier equations and modify them based upon that, we see a similar equation in this case too, where we just have fixed and loading, or fixed and variable time. And in the case where we're looking at the velocity in the hull direction while loaded, and that's what that means. The VR is return, is the velocity in return or empty direction. WF is the weight when fully loaded, and WE is when it's empty. V is the variable time distance that we just calculated or looked at a second ago, and D is the hull distance miles, so you're able to get the velocities again. And the variable time that goes with those two particular velocities, VH and VR. Once you know V, that variable time, then you can go ahead and calculate instantaneous cycle time by equation 5.2, which is C. V is that variable time. F1 is a sum of all the fixed time components. Again, we looked at those a couple minutes ago. And L is the distance that we're going. You're able to go through, and what the real bottom line is that we're looking for P, which is the productivity. And again, that's a function of the shift length, how many hours a day that you're going to be working in hours. SH is the capacity of hull, again in either tons or cubic yards. And then we see the sustained cycle time and the number of vehicles, okay, so that you can go ahead and get, again, a feel for production. So example 5.3 gives us a picture of this. Say you've got a hull length of 1,300 feet and a loading time of 3 minutes. You've got a variable time of 4 minutes, and we want to do a couple things. We want to compute the sustained cycle time, determine the optimal number of hauling units, and a sustained production rate. So if a hauler has a capacity of 20 bank cubic yards, BCY, if the shift is 8 hours long, and you waste about 2 minutes per cycle time, if you use the formulas that we looked at in table 5.1, you'll get a fixed time component of 7 minutes. Okay. Then if you go to equation 5.12a, which gives you that instantaneous fixed time, F1 or Fi is 7 minutes minus 2, which is the waste time per cycle. It gives you 5 minutes. So 7 comes from the table, from the equations in table in 5.12a, and 2 is that waste time, right? 5 minutes is the instantaneous fixed time. So then we can go ahead and calculate C, which is the 5 minutes, plus the 4 minutes of variable time. So you got fixed time and variable time. Okay. Then you got 3 minutes of loading time. So it tells you that total cycle time is 12 minutes. And if we know the total cycle time, 12 minutes, and the loading time, 3 minutes, it tells us that the optimal number of units is 4. So then we're going to be able to go down and calculate CS, C sub S, which is 12 minutes plus 2, which is the waste time, that gets 14 minutes. And if you could then go to the productivity, the sustained productivity number, you have 60, which is a conversion, times 4 units, times 20, times 8, divided by C sub s, and this is equation 5.14, it'll tell you that you can have, and 8 is the hours, okay, so we know where we're going. Your sustained production is 2,743 cubic yards per shift, and that's using 4 units. If you really stop and think about what's happening, if you're looking at earth-moving systems, the fact is the productivity is limited by how much production you get out of the loading facility, right? You can have an unlimited number of trucks, but you can only fill them as fast as the loader can fill them. No matter how fast they can make their haul and return, it still depends on how quick the loader can fill the trucks to keep them moving along. For example, in 5.4, if you have a front loader with a 1.5 bank cubic yard bucket, it has the following characteristics or cycle characteristics, right? The time to move to the stockpile, and this is the beginning, is 0.05 minutes. Time to fill the bucket, and it's not instantaneous, it takes pushing and shoving, it takes about 0.1 minute. So at about 6 seconds. Then you're going to move to the truck from the pile, and you maneuver to load, and that takes 0.15 minutes. Then you dump the loaded bucket into the truck, 0.1 minutes. Again, it just doesn't go instantaneously. Often you have to bang the bucket or move the machine so everything comes out of the bucket. In any case, you'll have a total cycle time, you sum all these up, of 0.4 minutes. If we look at something called a constructed load growth curve, which is in 5.1, we can see that there's also some non-productive time, 0.3 minutes of non-productive time and 0.1 minute of productive time that we have. And we'll take a look at that here so we can see that better. So let's take a look for a second at the constructed load growth curve that we were just talking about. And this curve has load size, that's for the bucket, bank cubic yards along the vertical axis, so 1, 2, 3 bank cubic yards, and then along the bottom is time in minutes. So if we look at that 1.5 bank cubic yard bucket, we see that it takes, 0.3 minutes, 0.1, 0.2, 0.3 of unproductive time, and then you'll see productive time appear as it goes up to the full capacity of another 0.1 minute, or a total of 0.4 minutes for that load size. This is a specific load curve for this particular piece of equipment. So you can look at all types of equipment and you have the same theory, that based upon the equipment characteristics, there's so much time of production and non-productive time that can be represented in that curve. So if you wanted to make one of these growth curves for a belt conveyor, and that belt conveyor has a productivity of, say, 2,000 tons per hour, you consider a couple things. First of all, that just like a truck, that belt has a time to accelerate to its operating speed. So 0.1 minutes, that the belt doesn't go automatically at its full speed. That will carry the 2,000 tons per hour. There's a tenth of a minute, or 6 seconds, that it takes to get up to speed. So what we're going to look at first is the steady state slope. We want to make a curve, so we want the slope, don't we? We've got 2,000 tons per hour. There's 60 minutes per hour, so that's 33.33 tons per minute. And if we assume that the average loading duration is 3 minutes, then we're able to figure out how much we're going to change that 33.33 tons per minute. And in fact, it's going to be 0.1, which is the acceleration time, isn't it? The time to get to operating speed, 0.1 minute. And 3 minutes is that loading duration time. So we're going to have a reduction of 0.03, or about 3%, because from this 33.33 sustained maximum, because the belt takes time to get up to speed. So if you want to consider a slope for design purposes, then you're going to take the 3% away. That's what we're doing right here. 1 minus 0.03, or 0.97 times 33.33, which is the maximum, tells us that the slope is going to be 32.33 tons per minute. So then we can plot that. Again, that's a straight line. And it'll show us, back here again, we're going to be about over the load, depending on the load time and the load size, the relationship for that particular conveyor. Again, you can do this for all types of equipment. Again, it's not necessarily that we're going to worry too much about this, but I think the whole point of this chapter is that you can develop a lot of empirical relationships that can help you make good estimates for work. And it's not just a matter of time of guessing or looking for 1 or 2 cycles and trying to figure out what's happening. There are ways you can go about figuring out the details that will give you a much better estimate. So again, to start bringing a whole bunch of things together, that's what example 5.6 does, and it gives us insight again into an operation. For example, if we have a 10 bank cubic yard BCY discharge hopper, that's a hopper where you load material in it and then it empties it into trucks or mixers or other piece of equipment, and you fill that hopper with a belt conveyor, and we just looked at the belt conveyor, and you load the conveyor with a 5 bank cubic yard bucket loader. So we started with the loader, didn't we? Then we looked at the conveyor, and now we look at the discharge hopper. We're starting to string things together. The productivity of the conveyor is greater than the productivity of the loader. Okay, so therefore the conveyor's productivity is limited by the productivity of its loading facility, which is that loader. The conveyor can't carry any more than the loader can put on it. So what the conveyor's productivity is really doesn't matter because it's limited by the loader. And if we're going to look at the hopper, which receives the material from the loader, then we can look at its cycle broken into 2 pieces. It takes, to fill the hopper, 0.7 minutes, and to discharge the load into haul units, about 0.1 minute. So we can, again, make a load growth curve for this situation. And it looks a lot like a bucket loader, and it should, because that loader is the constraint on it's getting filled. And when we look at it, we'll see the 0.7 and the 0.1 reflected. Here's the 0.7, then 0.1, 0.7, 0.1. And you can see that curve looks a lot like the loader, because the loader is the real limiting factor there. So again, using Phelps' approach, we have another way of determining the optimum number of haul units. and it takes the idea of that fixed and the variable times along with the load growth curve, and you can get that number of optimal units. How do you do that? Well, you start by determining the maximum velocity, and we go back to equation 5.9 and 10. And then you compare those velocities to the maximum allowable velocity. And in this case, what we're talking about is, say, the legal speed limit or some other velocity constraint you might have in the site. There just might be drivers can't go any faster than 10 miles an hour because the site's congested or for some other reasons. So then you're going to use that constraint to determine the actual velocities to be able to used in the travel time calculation. And that's T. 88 that you see in the equation is a conversion, right? 88 feet per second is the conversion to miles per hour, back and forth. Velocity haul, velocity return, as we had before. Loading time, you get off your load growth curve, constructed specifically for that facility. You see, you can make a curve for any type of facility that you have, or combination of equipment. Delay time D is an estimate. Again, you could measure that or again, use a factor, although it's probably better if you can to actually use a watch and calculate it. These are added, you add them all to the travel time, and you're able to calculate the instantaneous cycle time. And going back to equation 5.4 and the optimal haul unit equation 5.5, cycle time, number of haul units. Now, n isn't usually a whole number, and so you have to round it. And depending on which way you round it, it's actually going to affect your maximum productivity. And think about it. And we'll look at it here in this, using this example, how it is critical, or how it makes a difference in how you round your number. Okay. For example, say we've got a 1.5 cubic yard front end loader, 1.5 bank cubic yards, isn't it? It's going to load dump trucks with capacity of 9 cubic yards. So the loader takes 0.4 minutes to fill and load one bucket, and the travel time in the haul is 4 minutes, and the dump and delay times are 2.5 minutes combined. Then you're going to get an L of 2.4 minutes, a total cycle time of 8.9 minutes, and that'll give you 3.71 haul units. And you aren't going to have 3.71 haul units. You're going to have either 3 or you're going to have 4. And which one you have, again, is what's critical to productivity and ultimately to unit price. If you round down that number, you'll maximize the haul unit productivity. That is, the haul units will not have to wait to be loaded. There'll always be some time where the loader is going to be idle, waiting for a truck to come up, but the trucks won't queue up and have to wait. If this is the case, you're going to have the productivity of 3 haul units, 9 times 3 times 60, 182 cubic yards per hour, and we went through this equation earlier. So that's with 3 haul units. If you round up, you'll maximize the loader productivity because it's never sitting waiting for trucks, but you're going to have haul units waiting for at least part of each cycle. And again, this assumes that the trucks do keep moving. One problem you often have on a real site is that the trucks bunch up and they travel all together, and you'll find that they queue up anyway even when you have an optimal numbers. But in that case, your productivity for the loader productivity is 225 cubic yards per hour. So you can calculate the productivity of 4 haul units, and you can actually go ahead and calculate the time that vehicles stop. And we're not going to spend a lot of time in this area. It gets to queuing analysis, and that's not what we're about here. But if you look at ultimately the productivity of the 4 haul units, which is the important thing, you've got 224 cubic yards per hour, right? As opposed to 182 cubic yards per hour for 3 hauling units, and 225 cubic yards, which is the productivity of the loader. So obviously 4 trucks allows that loader to keep working, okay, significantly. Now, where the difference becomes important is if, depending on the cost of the equipment that you have, that difference in productivity and how much time equipment waits or sits, that's what we're really interested in. So if we carry on our analysis another step, and that's what example 5.8 does, we have a 1.5 cubic yard front end loader, and it has an hourly cost of $150 with the operator, so that's the machine and the operator. And cost includes the cost for overhead, which is the supervision. If also you have dump trucks that are $50 an hour with a driver, and that's about right, about $25 for each piece of equipment. And you have an instantaneous cycle time, C of 8 minutes, and the loading time is 1.5 minutes per truck, and the size of the truck is 10 cubic yards. And if you have 10,000 cubic yards that you need to haul, and the bid unit price is $2 per cubic yard, first of all, what you need is to figure out N, the number of haul units, and that goes to the cycle time, 8 minutes, and the loading time, 1.5 minutes, right? N equals 8 divided by 1.5, or 5.33 haul units. Then the total cost to complete the project can be described by equation 5.17. Total cost, M is the project quantity, and you have the cycle time and the instantaneous cycle time, the number of haul units. Number of haul units, the capacity of the haul units, and conversion factors. If you round N down to 5 units, you'll find the total cost is $10,667 to move that pile. If you round up to 6 units, again, you got another truck, but you probably have better productivity with the loader. The total cost is $11,250 to move that pile. You're expecting total revenue for the project of $2 times 10,000 yards, or $20,000. So in this case, with 5 trucks, you're going to have a profit of $20,000 minus $10,667, or $9,333. Or if you have 6 trucks, then you have a profit of $8,750. You see, in this case, it's better to round down actually, because you make more profit, and that's because you do have fewer trucks, and the cost of that truck and that extra driver makes a significant difference in the overall productivity costs. So I guess we use a lot of rule of thumbs in our work, especially when you're on a job site, and the authors make a point of talking about one rule of thumb, always round down, since it's easier to add another truck if you need to than to delete one. And that's important because it's very difficult to send a truck home and a driver in the middle of the day. Often you just can't do it. Depends on if you're union or non-union, or the contract arrangements, or just trying to keep everything fair. And so, again, as I was pointing out a couple minutes ago, you never make arbitrary decisions about the number of trucks. You have to consider time, equipment, labor to make that decision. And consider more than just a whole series of rule of thumbs. The best rule of thumb to follow is just don't make an arbitrary rounding decision. That makes the most sense. The rest, you should at least use some of the equations or put some of the thought into those equations into your decision making. Besides the number of trucks, another important factor, especially if you're loading trucks, is the size of the truck. So if you have, again, a front end loader we've been using with that 1.5 yard bucket, and you want to haul material from a stockpile, and we go back to that first growth curve that we looked at, 5.1. If we need to haul 10,000 loose cubic yards of material, there are 3 sizes of haul units available to the equipment manager in this case. And there's a table, 5.2, on the next page here, and we'll look at that one. You can see the different haul units and the different characteristics. Haul unit A can haul 6 to 8 loose cubic yard, B 12 to 14, C 15 to 17. As the capacity gets bigger, you need more horsepower. Efficiency stays about the same because that depends more on how you take care of the trucks and the drivers. And if you have an organization, the trucks will be the same. Probably your drivers are going to work together as a team, and they'll have the same kind of efficiency. You see that the larger the capacity, the more the vehicle is going to weigh, both full and empty. And you see that the operating costs and the maintenance costs go up also as the vehicle capacity gets bigger. Labor stays the same. You generally pay your drivers the same whether they drive a small truck or a big truck. What's this? And the maintenance and the equipment operating costs and the maintenance costs relate to how much fuel you end up using. And with a heavier vehicle and a bigger engine, you generally are going to be using more fuel in that vehicle, although when you apply that fuel cost across to the capacity or for each cubic yard, it may go down because you get better productivity. Again, it depends on the situation that you're working in. So anyway, if you have 3 different trucks to choose from and you want to figure out what's the best size, especially if you consider that you may be hauling over a haul road that is about 5,000 feet long, 10,000 feet both ways altogether, and you have a 60 pounds per ton rolling resistance, and it has a slope of 2% in haul direction. So that means you're going to work harder in the haul on the way back. You're going to be going down slope. If the unit weight of the material is 3,000 pounds per loose cubic yard, again, we looked at a table earlier, one of the earlier chapters. That has a speed limit of 35 miles per hour. So again, we were talking about a speed constraint in the earlier example. In this case, it's 35 miles an hour. And the cost of the truck driver is $15 per hour, and that's in the table. then we have the information we need to be able to go ahead and calculate which is the best size truck to use. Again, we go back to those earlier equations, 5.9 and 5.10, and substitute our values in there. We're going to find that the velocity for the haul is 18.47 miles per hour. And we can do the same thing for that return. And the author has the wrong number here, just so we know. 187.93 miles per hour isn't quite right. It's actually 35 miles per hour. And so if we have a velocity max of 35 miles an hour and a haul velocity of 18 miles an hour and a return velocity of 35 miles per hour, then we can figure out the time, and it's rounded off to 4.8 minutes. And then if we go to figure 1 and enter that load growth curve for 6 cubic yards for haul unit A, and we'll find that A is 1.6 minutes. And then we can estimate all the delay times from the earlier equations that we had. Altogether, we'll find D is the total delay 1.9 minutes. Then we can go back in equation 5.4 and find that that total cycle time is 8.3 minutes. And then we can go back into equation 5.5 and find that 5.19 units for that particular truck, the smaller truck, is the optimum number of units. So we can, again, if the maximum achievable system productivity is the productivity of the loader, you can round up to 6 units. So each truck will have an additional time waiting. Okay, you're going to have more trucks than the loader can service, and so the trucks have to wait. And you'll find that the additional waiting time is 1.3 minutes. Again, I don't expect you to do this. We're talking about an example, though. And so we're wasting driver time, right? Because they're sitting around. And it's going to be about 2 minutes per cycle. So altogether, the total cycle is going to be 11.8 minutes. And then what we're able to do, it's 11.6 minutes, I'm sorry, 11.6 minutes. So then what we're able to do is determine how many hours of hauling we'll need to move that 10,000 cubic yards for 53 hours of hauling. Okay. Then we can go ahead and so once we know the total hours of hauling, we're able to come up with a cost index number. And that relates to the time and the costs, the total amount of material being moved. And in this case, the cost index is 2.58. If you go back through and repeat the same set of calculations for haul units B and C, you'll find that the cost index for B is 2.13, and the cost index for C is 2.12. Again, you can also look at it in another situation where you can add sideboards, and sideboards are at the top of a dump truck's box. they allow you to put material. Remember I told you earlier about putting more material in the vehicle, and that it can cause some later maintenance problems if you overload the truck. But in any case, it's one way of getting more capacity. So if you add more material in each load, you're able to get, again, some slightly different cost index information. So the real bottom line is that you can take the cost index and the number of pieces of equipment, and you can plot the cost index number versus the haul unit capacity. And all it really says is that if you start out with a haul unit of 6 yards, you have a relatively low cost, or haul capacity gives you a high cost index number. But as you increase the haul unit capacity, that cost index number comes down and really minimizes out at about 13.5 yards haul unit capacity. After that, even having a bigger truck with more capacity, because of the extra cost to the vehicle, and your cost index goes back up. So if you're looking to find the lowest price, you're going to look at a vehicle that has that 13.5 yard load. And if we go back to table 5.2, we'll see that haul unit B has a capacity in that particular cost range. So haul unit B is actually the most efficient vehicle to use in this case. So I think for these last several examples, especially, again, what I want you to take is not, and we're not going to worry about you being able to calculate these particular items, but I want you to remember that it is, there are a lot of factors that can go into calculating the capacity and the efficiency and the productivity. And that when you are looking at a job site, that you should make sure and consider those factors in laying out a site and in trying to plan for work on that site.